random environment.
Okay, thank you very much. It's great to be here, first time at CMAT. So I realized recently that I have plenty of time, so I changed the title of my talk. It was originally on directed polymers on the complete graph, but I will talk also about another mean field model of directed polymers. I will spend today's lecture to review some well-known results and give some proofs. And on Thursday, I will give more of a regular talk. So today, I will start talking about directed polymers on ZD. So this will overlap a bit with the talk of Kostya gave yesterday. So I will just review some of the main results and to set the problematic. Next, I will talk about, let's say, a simplification, directed polymers on the tree. Okay. So in this case, one can give a complete characterization of the phase transition. I will hopefully give you a complete proof of the phase diagram of the model. And then on Thursday, I will talk about a recent work with Alejandro Ramirez and Francisco Metz on directed polymers in random environments on the complete graph. Okay, so let's start about the original model, the model on ZD. So to introduce the model, we need two basic ingredients. First, the path space. So this will be S, a simple random walk on ZD. I will denote its slow by P0, so it's a simple random walk that starts on 0. And next, I have to introduce the environment. Which is simply a collection of IID random variables indexed by time and space. Time is discrete, space as well. And I will always assume that these random variables have finite exponential moments. And I will denote the law of this family by P double bar. So next, once I have the paths and the environment, I will introduce the energy of a path. So this will be the sum of all the random variables encountered by the path. So Hn of S is the sum of t running from 1 to n of omega t st, where st denotes the position of the walk at time t. So once I have this, I can introduce the polymer measure. So the measure of a path will be proportional to the exponential of beta times the energy of the path. Okay. And then I have some renormalizations to make it into a probability measure. And also for simplicity, I will add here just 1 over 2d to the n, the probability of a single path. So here, the n, the normalizing constant, is known as the partition function. And it's just the following quantity, 1 over 2d to the n, sum over all paths of length n of exponential beta the energy of a path. So one way to see this is on the following. So for me, time will go in the horizontal direction. The transversal direction will be ZD. Then the paths will be just these simple random walk paths. And you can think that at each side of the lattice, you attach a random variable omega tx. So that's the model. Is it clear? Okay, so this model comes from physics. So let's talk about a little bit about the history of the mono. It was introduced by Henley and Hughes in 1985. So what they were doing was to study some, let's say, some spin models in disordered environments. So the situation is roughly the following. So let's say you have a two-dimensional Ising model, and you engineer boundary conditions in such a way that you have coexistence of phase. So you put boundary condition plus on the upper side of this box, boundary condition minus on the lower side. Then if you choose the temperature appropriately, you will have coexistence of phase. You will see an interface that separates the phase of plus and the phase of minus. Okay? So if you don't put any disorder, if you consider the usual Ising model, what was proved is that this interface converges to a Brownian bridge. Okay, so of course this is not a directed interface, it's not just a height function, it has some overhangs, it can backtrack. But in some scaling limits, it indeed behaves like a height function, and the scaling limit is given by a Brownian motion. Now, what you can do is introduce disorder by diluting the interaction between neighbor sides. So the interaction between neighbor sides in the Ising model is just a constant, is 1, but you can think that you associate some positive random variable jxy to each neighboring sites, and then the interface will try simply to go to regions that are energetically favorable. It will try somehow to minimize the weight of the edges it crosses, and then a new phenomenon will arise. So there will be some kind of competition between this entropy effect that tend to make this interface converge to a Brownian motion to another phenomenon produced by the environment of this interface trying to pin itself to regions that are energetically favorable. So what Henley and Hughes conjecture is that somehow in a certain scale, again, this interface will behave like a height function, and it will indeed behave like a random walk in a random potential with only local interactions. So that's the genesis of the model. As far as I know, there is no rigorous mathematical result that make the links between this diluted Ising model and directed polymer, but that was the origin at least. So the model reached the mathematical community in the work of Imbrie and Spencer in 1988. And a little bit after that, it was the work of Bolthausen in 1988, which will be more relevant to us. He introduced some Martingale techniques, so we will have the opportunity to review these on the tree. So these are the main techniques that were used afterwards to work on the phase diagram of the model. Then there was a series of work until the year 2000, and then between 2000 and 2010, I will say there were mainly two teams working on this model. So first, Carmona and Hu, and on the other hand, Comets and Yoshida, another of course, which delucidated the phase diagram of the model. So we have a pretty good understanding of the model. So historically, so Carmona and Hu worked mainly on the Gaussian setting. Then this was generalized by Comets and Yoshida for more general environment. So again, I'm not giving a complete list of reference, but this will be the main reference that will be relevant to us. So the main object of study is the free energy. Which is defined as the following limit. P beta is the limit when n goes to infinity of 1 over n logarithm of the n omega beta. So this is the positive temperature analog of the passage time we heard about yesterday. So this limit, of course, is random in principle, but it turns out it is not. It is a constant that depends on beta and on the law of the environment, and there is a standard program to show the convergence of this object. So here, this quantity is not subadditive or superadditive by itself. It's a point-to-line object, so there is no direct subadditivity. What you can do instead is to look at the limit of the same quantity, but first you average with respect to the environment. Then you can show that that quantity is subadditive. So for that, you use the standard Fekete lemma, standard subadditive lemma. This will converge to a number. And then to go from the limit of this integrated quantity to the random quantity, you use concentration of measure. Okay, so it's a two-step procedure. First, you look at the integrated object. You use additivity, so that's the easy part. And then you have to manage to use some concentration of measure tools to show that the non-average object converges to the same limit. So let me first give a bound on this quantity, which is an easy consequence of Jensen's inequality. You can bound P of beta, but what you would get by just commuting the logarithm and the expected value. So that's just by convexity. And this is something you can just compute by independence. So you are computing the expected value of this quantity. So everything is IID. The 2D to the n cancels with the number of terms in the sum, and you just end up with the expected value of beta times the energy of the path, of any path. But again, this is IID, so it's just a product of expected value of exponential of beta times a single omega. So this is simply expectation of exponential of beta omega with the log, which is a quantity that we will denote by lambda beta, which is also known as the annealed free energy. So that's a completely general inequality. So this quantity is finite because they assume from the start that these random variables have finite exponential moments. So a very natural question is to ask whether these two quantities coincide or not, and also, well, if they coincide or if they do not, does that imply something or mean something with respect to the polymer measure? So very intuitively, what does it mean if P is equal to lambda? What it means, yes.
When you say omega, do you mean the sum of the environments, or? I mean the random variable that you put there.
Yeah, it's a bit of.
I mean, maybe it's just to make clear things in my mind. Is when you say W, do you mean the whole path of the up to?
The path is S. No, there is an abuse of notation. I'm using omega for the whole environment, and also for a single random variable.
Okay.
Yeah.
Okay.
Yeah. Let's say omega 1, 1.
Okay.
So, yeah. Yeah. Okay. So intuitively, if P is equal to lambda, this means that everything behaves like there is no disorder. That's what we would get, for instance, if the disorder was concentrated on the single value. Let's say there is nothing special happening if P is equal to lambda. On the other hand, if P is strictly smaller than lambda, there should be something interesting happening. Let's say the correlation of the model will be producing something different that would make this strict inequality occur. And that's actually the first phase transition that you study on this model. You characterize the region where P of beta is equal to lambda of beta, or the region where there is a strict inequality.
In that inequality,
Yes.
P means what? The first or? I'm confused. What's the meaning of that inequality?
Of the first one?
Yeah. So the definition is the one that it's upstairs?
Yes.
The one that depends on omega?
Yes. So as I said, the limit does not depend on omega. Yeah. So yeah. So it's a two-step proof. So first you integrate the quantity on the bottom does not depend on omega anymore. Then you show that converges. And then you hope that the random quantity is reasonably close to the non-random quantity. And for that, you use concentration of measure. Okay, so let us state the first theorem. So this theorem is a blend of resolved by all these people. So the situation as we know it now is the following. So there exists a value beta critical bigger or equal to 0 such that if beta is smaller than beta critical, P of beta is equal to lambda of beta, and if beta is bigger than beta critical, then P of beta is strictly smaller than lambda of beta, and here I should add that. Okay, so this is more or less the situation that Kostya told you about yesterday. So if beta is small enough, you have a situation that he called weak disorder that coincides with the region where the polymer under the polymer measure is diffusive. I will not talk too much about the path properties. I will concentrate more on the free energy, but there is a parallel between these two phase transitions. And then if beta is big enough, you will have the region where there is localization, which is known as strong disorder region. And you can show actually that the transition is sharp. That there is a critical value that separates these two regions. That's a result by Kometz and Yoshida. So it's a very nice just derivative argument. They can show that P minus lambda is an increasing function. So if at certain point they start to be different, they stay different forever. So there is no reentrance phase. So let me say then as an observation that this phase transition can be characterized in terms of also of localization, delocalization of the polymer measure. Okay, so maybe one more word about that. So what is proved is that on the whole weak disorder region, you have an invariance principle for the paths under the polymer measure. So this was known, I think, in some versions since the work of Imri and Spencer and Bolthausen, at least in a very restricted part of these regions, the so-called L2 region. And then this was improved later by Kometz and Yoshida to an annealed version of the central limit theorem in the whole weak disorder region. And then also in the strong disorder regions, there are results of Kamen and Hu and Kometz and Yoshida, where you can show that the polymer measure as atoms. So they are favorite sites that carry most of the mass of the polymer measure. So let's go back to beta critical. So what do we know about beta critical? In fact, not too much, beside the existence. Well, there are only two cases where the exact value is known, which is in dimension 1 and 2.
You know it's finite.
Sorry?
Would you know it's finite?
It's not necessarily finite. Yeah. You can engineer some environments which have, I think it's big enough mass at the essential supremum of the distribution in such a way that you can show it's infinite. So what you can show is that in dimension bigger or equal to 3, this beta critical is strictly positive. So there are some L2 computations that you can do and use some simple random walk arguments to show that this is positive. And in d equal to 1, you can show that beta critical is equal to 0. So this is a result of Comets and Vargas. From 09. So this goes back to, I think, at least 1089. So what they do is that they compare the model with the model on trees, on some variants of the tree. And then is it 09? 06, sorry.
I think so, because it was his PhD thesis.
Yes, yes, it was in, yes. And then the case d equal 2 was delucidated by Lacoin. In 2010. And that's basically all we know. So for instance, there is no clue on what would be the exact value of beta critical in dimension bigger or equal to 3. Okay, so we make an observation and we introduce this martingale I talked about a few minutes ago. So this will be an important object for us. So I will define omega wn. I'm dropping the dependence on omega and beta, so there should really be an omega and beta there. Which is a renormalized version of the partition function. So this is nothing else but the n times exponential of minus n times the annealed free energy. So it's easy to see that this is a martingale with respect to the filtration Fn, which is just the filtration generated by the environment for times up to n. Okay? So it's not just a martingale, it's a positive martingale. So in particular, it converts to some limiting random variable.
Basically, you're fixing the environment, yeah?
Yes, I'm fixing the environment. Yeah. So it converts to a positive random variable. And you can see the following. If for some reason you know that omega infinity is positive almost surely, then you can say something about in which region you are. It's just a very simple computation. So remember that, so let's look at the limit when n tends to infinity of 1 over n log omega n. So now if you know that omega n converts to something strictly positive, this is an order 1 quantity. So this limit is just 0. But on the other end, this limit is just p of beta minus lambda of beta. So you are in the weak disorder region. Okay? So this is something we will see in a few minutes. So W infinity turns out to be a tail random variable, or let's say the events that omega infinity is bigger than 0 is a tail event, so it has a probability 0 or 1. So this says that if for some reason you know that the omega infinity is not vanishing, that you are in the weak disorder region. So you can actually give another or define another phase transition, so you can define a new region of weak disorder which corresponds to the region where omega W infinity is strictly positive, and a strong disorder region where it's equal to 0. So you know that there is a relation between these two notions of phase transitions. So if, as I showed you, if omega infinity is positive, then you are in the weak disorder region. So you would like to say that if omega infinity is equal to 0, then P is strictly different than lambda. And unfortunately, that's an open question. Because to ensure this, you would have to know something on the rate of decay of omega infinity. So for instance, if you know that it decays exponentially fast to 0, then you're basically done. But that's something we don't know. And that's actually the idea used by Lacoin to show his results. So he used some fractional moments method. He was able to show that there was exponential decay at this level, and he obtained the strict inequality between P and lambda. But again, in the general case, it's something we don't know. Okay, so this was just to settle the problematics. So now I will turn to the model on the tree. And this is a situation where you can give a complete characterization of this phenomenon. You can give a precise value of beta critical. Okay, so now we consider TB a rooted regular tree with branching number, with constant branching number equal to B.
So,
yes.
I have one question before you.
Yeah.
So what happened when W infinity is equal to 0? Because in that case, you may expect like different behaviors depending on the environment, or
well, the conjecture is that when W infinity is equal to 0, you are in the strong disorder region and you have a localization. But it's not known. Okay, so the environment now is an IID family of random variables indexed by the size of this tree. Again, with a finite exponential moment. And now the set of paths will just be paths that go away from the root. So for S directed paths, you again define the energy of a path as the sum of all the environment random variables along its trajectory. So now it's simply indexed by the size of the tree, so there is no other dependence on t there. It's still directed. And then we can write down the expression for the partition function. So it will be, again, a sum over all paths of length n of exponential beta hn of s. Okay. So again, you can define the free energy. You will have the same inequality than we had before.
In the other case, in the first case, the random variable is dependent also on time. Now
Yes, but no, so time is correspond to the generation of the site in the tree. So I take S, a path that always goes away 1 unit from the root, so time is encoded there. Yeah.
And trees are not necessarily random, right?
No, this is
These are fixed.
it's a fixed binary tree. Yeah. Okay. So again, we define the free energy just as before. And this is again small or equal to lambda of beta by the same reason. And again, you can ask whether P is equal to lambda or not and try to characterize the point where that separates the two regions. So before going to that, so that's something I think I will have time to prove completely. So there are two motivations to study this model. So as I introduced, it is just a simplification of the ZD case, right? You replace ZD by the tree, and let's see if we can say something more. But actually, the exact same model appear in two unrelated contexts. So the first context was branching random walks. On R. So the setting is the following. You start with one individual at the origin, and then the rules are the following: set at each integer time, each individual splits into B children. Okay, so let's say you start with your single initial individual, then at time 1 it will split into B individuals, and each of these will make a random displacement. So at time 1 you just erase this one, and you position its children according to random positions. So each of them performs a jump with slow omega. Okay, so at the next integer time, this individual splits into 3 other individuals. So that's, you have 3 particles here, so that's this one and this one. So each time it splits, you just distribute the children at a random position relative to the position of the father. And no individuals are naturally encoded by sites of the tree TB. And now what the random variables omega represent is the relative displacement of a children with respect to its father. So the energy Hn of let's say, yes, of u. So let's sum, I don't know exactly how to write this, but let's say on the tree, you can completely characterize a path by just giving its final point. So let's say this is the energy of the unique path that has u as a final point. So what this is just the sum of all the omegas over the trajectory of this path, or the sum of all the omega over all the parents of u. So this is just the position of the individual u. So in this context, Wn is known as the Biggin's Martingale. And this goes back to 77, so it's a Martingale naturally associated to this kind of model, which encloses some properties of the model. Okay, so that's how the model arrives in at least one field, which was in principle independent. And there is a second origin of the model, and this is known as multiplicative cascades. This is a model introduced by Mandelbrot. So this was a simplified model for turbulence. It goes back, I don't have the exact reference, but I know that it goes back at least to Yaglom, and I think Kolmogorov has also some work on this. So you will see the setting is quite different. So let me tell you about the model. So let's take b equal 2 for simplicity. You can do it for any b, but just stick to this case. Then call In the following collection of intervals. So it will be just a dyadic partition of the interval 0, 1. So here k goes from 0 to 2 to the n minus 1. And call I the union of all these families. And next we will associate a positive random variable to each interval in this collection. So these are positive random variables with mean 1. And next, by an induction, you introduce a family of random measures as follows. So start with mu 0 equal just the Lebesgue measure on 0, 1. Next, define mu 1 as just the random variable u0, 1 multiplying the previous measure. Okay, so you just weight randomly the Lebesgue measure on 0, 1. Next, you define mu2 in two cases. So if you are in the interval 0, 1/2, you weight mu1 by the random variable corresponding to the interval 0, 1/2. And on the complement, you just weight it by the random variable associated to the interval 1/2, 1. And you continue with this construction. So at each step, you take the measure you constructed in the previous step and you weight it by the random variable corresponding to the interval you're on. So inductively, so just in words, mu n plus 1, it's the measure that agrees with ui mu n on the interval I in the collection In. So equivalently, you can write the density of this measure, so call it Un, where Unx is just a product of these random variables, where IGX is just the interval I that contains X. So you just keep track of, let's say, just the dyadic representation of X. And based on that, you have this product of random variables. So you can see it's, again, if you write U equal exponential of beta omega, this is exactly the exponential of the energy of a part in the construction with a tree. So it's a theorem by Cahan and Perrier. So this goes back to 76, is that these measures have a limit. Okay, and studying the limit of this measure is intimately related to studying the limit of this Martingale Wn. So it's just really the same model, but in a different language. So let me briefly describe other things you can do with that. So under certain conditions, which in the language of directed polymers would be some weak disorder condition, you can show that mu has no atoms. Okay? So now you can define a metric on 0, 1 by just considering the measure of the interval xy. So this is a random metric. And there is a work by Benjamini and Schramm from 2009, where they find a relation between the Hausdorff dimension with this random measure and the Hausdorff dimension with the standard Euclidean metric. So it's a formula that relates the two quantities. So you take a compact subset of the interval 0, 1. You compute his house of measure on the one hand with the random measure, on the other hand with the usual Euclidean metric, and there is a relation. And this is known as the KPZ formula. So don't get overexcited. This is the other KPZ. So now I really need my notes, because writing the name, well, the name of these guys is a kind of a nightmare. Yeah, but you're cheating. So this is after, I won't even try to pronounce that. Okay. So this is kind of a very basic version of very general theorems people have been working on. So there is all this work by Duplantier and Sheffield and etc. So it's related to these things, and then in some indirected way to polymers on the trees or on tree-like structures. Okay, so let's go back to the polymers.
Can you translate this result by Benjamin and Schramm to polymers? What does it mean there?
I don't know. So that's not the kind of question you ask for polymers. Actually, no, I don't know. Yeah. Okay. So now what I want to show is I want to compute the free energy on the tree. So first I need the following observations. It's a very simple lemma that should not be surprising. It's the 0-1 law I mentioned. I already mentioned. So the probability that omega W infinity is equal to 0 is 0-1. And it's a very simple proof. Actually, the proof, I will give it on the tree, but it works just as fine on RD, ZD. So it's based on the recursion satisfied by the Martingale or the partition function. So omega W n plus 1 is a sum of exponentials of energy over the paths of length n plus 1. So over all the paths that are represented there. And then you could do the following decomposition. You could decompose according to the first step of the walk. So there are B possibilities. Okay. So once you choose the first jump, you collect the random variable E beta omega j. So just indexing this random variable by j. You are dealing with the Martingale, so you have an extra contribution of minus lambda beta, and then you keep summing over the rest of the paths. So what you will see is exactly a random variable that has a law Wn, but now you will have one Wn if you made this upward step, and another one if you make the downward step. Okay, so they are indexed by j, they're just shifted version of Wn. And moreover, they are independent, because they just live on different regions of the tree, and the environments on these regions are completely independent.
In ZD, that wouldn't be the case, right?
Yes, that would not be the case. No, there's no problem. You will see. It's just a side comment. And you can iterate this relation. Oh, there is an extra one of a b that comes from our convention. So you can iterate and you get the following. So now it's the sum over all paths of length k. So now you are not decomposing just according to the first step, but according to the first k steps. And then you get a contribution for the first segment of beta energy of S minus k lambda beta. And then again, you have this shifted version of the Martingale, but now based at the final point of this first piece of work. And then you just take n going to infinity, and you get that Wn is, well, the first part of the expression will be exactly the same. But now instead of having this Wn, you will just have a shifted version of W infinity. Okay? And this is for all k bigger or equal to 1. So now the event W infinity equals 0 is exactly equal to the event that all these shifted versions of W infinity are 0. And that's again for all k bigger or equal to 1. But now this is independent of the environment over the sites up to generation k. And that's for all k. Okay? And that's also true on ZD. Okay? So it means that if you look at the sigma algebra generated by the environment on the finite part of a tree, this will be independent of this event. So W infinity equals 0 is a tail event. So by the standard 0-1 law, its probability is 0-1. Okay, so that's really practical because if you want to know that, for instance, that W infinity is positive almost surely, you just have to show that it's positive with a positive probability or compute some moment and show that the moment is positive. That's something we'll use. Okay, so now I can state finally the theorem which will give the characterization of the free energy on the tree. Okay, so this is a blend of result of Kahn and Perrier, same paper from '76, and so that's one half of the proof. The other half is provided in a paper by Buffet, Patrick, and Poulet in '93. So let's beta critical.
So this paper by the first one, 176. That was about these cascading.
Yes, yes. So actually, they need to show that W infinity is strictly positive. That's the part of the proof that they look at. So you define beta critical as the unique root being 0 infinity of the following equation. if it exists. So you can show that this is a monotone quantity, so it has one single root. And you define it as plus infinity otherwise. So that's the beta critical. Then you can give the exact value of P of beta. It's equal to lambda beta if beta is smaller or equal to beta critical. And it's equal to beta lambda prime of beta critical minus log B if beta is bigger than beta critical. Okay. So the free energy coincides with the annealed free energy up to this explicit beta critical value, and then it becomes linear. And that's a crucial difference between the model on the tree and the model on ZD, is that on ZD you can show that the free energy is strictly convex, and here it's just strictly convex on the weak disorder region, and then it becomes flat. Okay. Okay, so let's go to the proof. So let's look first at the weak disorder region. So this is the part provided by Kahn and Perrier. And this used the Martingale techniques and the subadditivity. So let's okay, so the proof is, let's say it just works. It works. There are some kind of miracle and some clever inequalities that make it work. It's maybe not very intuitive. The other part of the proof is more convincing in a sense. So let's just recall this basic concavity inequality. That if I take alpha between 0 and 1, then I have the following inequality. This is for alpha between 0 and 1, and xj positive. So that's just concavity of the function x to the alpha. This is very useful in polymers. That's, believe it or not, this simple inequality is the basics of the metal fractional moments that I mentioned before. But unfortunately, here we would love to have a reverse inequality. And it turns out there is one. So this is by Cahan and Perrier, which says the following. So you can bound this below by this same quantity. But of course, you have to subtract something. And then you get the reverse inequality. Okay, so it's let's say showing that it's a piece of calculus. Now let's apply this in our context. So let's recall our recursion. So we have Wn equal 1 over b. Sum j goes from 1 to b. Exponential beta omega j minus lambda beta. Wn minus 1j. Okay. And let's just apply this inequality and integrate with respect to the environment. So on the left-hand side, we will have just the fractional moment of Wn. And here, well, I pick up 1 over b to the alpha. Then I have to integrate the alpha powers of all these things, so they have all the same distribution, so I collect an extra b. When I integrate this quantity, what I get is exponential of lambda alpha beta minus alpha lambda beta. And finally, the fractional moment of Wn minus 1. Okay, that's the first piece. Then comes the rest. So you have 2, 1 minus alpha. Then again, all these terms have the same distribution. They are b times b minus 1 of them. And then we have to integrate these cross terms that are independent. So each of these xj will be one instant of this random variable. When you integrate 2 of them, it's just product of the expected value. So first, the piece that comes from 2 copies of this random variable, what you get is exponential of, so you don't have to forget the 1/2. And this is square because we have 2 of them. And next comes the fractional moment of Wn minus 1, but now it's power alpha over 2, and there are 2 of them, so we have a square. So that's what it is. I will spare you the algebra. Just tell you that you need to use 2 facts. You can make the computations if you really want to. So first, by concavity, Wn to the alpha is a super Martingale. Which in particular means that these fractional moments are decreasing. Okay. So use that to replace this n minus 1 by an n over here. And next, the other annoying thing in this expression is this 1/2 which is there. And that you can handle by convexity. And convexity tells you that twice lambda of r over 2 is smaller or equal than lambda over r. So use that to replace these 2 lambda of whatever by a lambda of alpha beta.
And the power to the alpha half, that's what problem?
No, that's not the problem. That one we will keep. So now I will spare you the algebra. And what you get is this.
So there seems to be a minus sign in front of it.
Sorry?
So there's a minus in front of the e to the lambda 1/2 alpha beta.
1/2 here?
No, in front of the number.
Yes, there is a minus.
So
I will put this guy on the other side. So actually, I want a lower bound on this guy.
I think that the inequality would go the wrong way.
Does it? I mean, if it's the case, it's...
Oh, because you're upper bounding
yeah.
the first one.
No, I will lower bound this one. Yeah. So then you will see that the alpha over 2 doesn't matter. It's pretty convenient, actually. Okay. Okay, so it looks bad, but but it actually will start looking pretty good when you take alpha growing to 1. Because you keep this b minus 1. This piece is converging to lambda of beta minus lambda of beta, so it just disappears. And here you get the expected value of w n minus 1 to the 1/2 squared. And now this ugly piece turns out to be a derivative, or minus a derivative, actually. So what you get here is log b minus b lambda prime of beta plus lambda beta. And when alpha goes to 1, you just get the expected value of wn, which is 1. And now you take n going to infinity. So this guy has the first moment, so in particular the power 1/2 makes it uniformly integrable, so you can go to the limit. And you get that if this quantity over there is positive, so if beta lambda prime, beta minus lambda beta is smaller than log b, then expected value of a certain moment of w infinity is strictly positive. Then you have with this out. Okay.
So I repeat my question, because if you put the minus thing to the other side, it becomes a plus.
Yeah.
It to be bigger than something, but in fact, the two number is smaller than something. So how can
You take this guy, you put it on this side, and then you just use this upper bound.
Yeah, but it has to be bigger than something. Am I crazy? I'm crazy.
Yeah.
No, I'm crazy.
We already suspected, so.
I agree.
Okay. So let's go quickly to the strong disorder region. So there the proof is more reasonable. Okay, so first a lower bound. I will show that lim inf of Pn omega beta is bigger or equal to beta lambda prime beta critical minus log b, where Pn is just the thing that converts to free energy. So there is a fact, an easy fact is that Pn omega is convex. It's really easy because you just compute derivatives. So you compute the derivative with respect to beta, and it's just chain rule. You take the derivative, you will get a 1 over the n. And then what you get at the end is just the average energy over the polymer measure. So that's a standard fact. It's an easy computation. And then if you take a second derivative, what you will get is just the variance of the energy with respect to the polymer measure. Okay? So the second, it's a variance. It's a non-negative, so it just gives you this convexity. Okay, then, of course, this is for beta bigger than beta critical. Okay, so then let's compute derivatives. Let's bound derivatives. So by convexity, then you can bound this derivative by any derivative at a smaller value of beta. Okay, so beta prime is something smaller than beta. And then you take the limit. And here you are allowed to take the supremum over all beta prime smaller than beta. And actually, it's enough to go up to beta critical. But now you are in the weak disorder region. So you know exactly what this, the limit of this Pn is. It's just lambda. So this limit is just lambda prime of beta. And you're still taking this supremum. Beta prime. And you can convince yourself that lambda is strictly increasing, so that's exactly lambda prime of beta critical. And next you integrate. Okay, there are exchange of limits and derivatives here that everything was fine because things are convex. So now you just integrate this inequality. In the limit, on the left-hand side, you get lim inf of Pn omega beta. So you are integrating, you have to write here your starting point, which is P of beta critical plus beta minus beta critical. And then here you plug the lower bound you got here. Okay. Now this P of beta critical, you know exactly what it is. It's just lambda of beta critical. And not just by definition of beta critical, this is exactly beta lambda prime of beta critical minus log P. So that gives you the lower bound. Okay, so I kept the prettier part for the end, which is the upper bound. And it's again a piece of convexity. So let's use the same inequality, let's say, but instead of using the derivative at something which is to the left, use the derivative at something which is to the right, and you get an upper bound. Okay, it's just convexity. And now you want to get an upper bound on this derivative. Now, as I said, the derivative of this free energy is 1 over n, then the average of the energy of the paths under the polymer measure. And that's the thing you have to bound. And then just use the most brutal bound that you can think of. Just bound this by the maximal energy of a path. Now I claim that I can control this quantity. So the lim sup of 1 over n h star n is small or equal to lambda prime of beta critical. Okay, so I will prove that in a minute. So with this, you have exactly the same expression we had before. So we take the limit here. It's more equal to the limit of this quantity, which is again lambda at beta critical, plus beta minus beta critical times the upper bound we got on this object, which is lambda prime of beta critical. And again, by the same thing we had before, this is beta, lambda prime beta critical, minus log b. Okay, so let's go to the proof of the claim. And again, this will be pretty brutal. So take A bigger than lambda prime of beta critical, and let's look at the probability that Hn star is bigger or equal to An. So let's just use a union bound. So we get a b to the n, which stands for the number of paths over which you are maximizing. And then the probability that the energy of any one of these paths is bigger than An. So this is just the probability of a sum of IID random variables to be bigger than An. So you can just bound that by large deviation by minus exponential of minus n lambda star of A plus maybe a small o of n, where this lambda star is the Legendre's transform. Okay, and you're basically done because this thing is strictly convex on its domain. So lambda star of A is strictly bigger than lambda star of lambda prime of beta critical. And again, that's something you can compute by just computing the derivative. This turns out to be exactly log b. So in the exponential, you have something that kills the b to the n. And you have that these probabilities decay exponentially fast for any A bigger than your target value. So you just use Borel-Cantelli. And that finishes the proof. Okay? So again, this can be viewed as I tried to convince you, this model came independently from different fields. It can also be viewed as a simplification or a mean field model for directed polymer, in the sense that what you are doing is really simplifying the correlation between the energy of paths, which are the problematic objects you have to deal with when you study directed polymers. So that's a mean field model. So there is another one that we studied recently with Comets and Alejandro Ramirez, which amounts to replacing ZD by a complete graph. So that's a different sport which is related to product of random matrices. And a special feature of this model is that we were able to find a special environment that makes the model solvable. And that's what I will talk about next time. Thank you.
Questions or comments?
Yes.
Yeah, I was wondering, you say the weights have to have all exponential moments. So what goes wrong if there's only like up to a certain A?
Yeah, up to a certain A, everything works. Yeah, you might have to check carefully in which situation you are in this case. But on DD, the program goes, at least for the sake of showing that the free energy exists, you can assume a certain a polynomial moments of a certain order depending on the dimension.
Polynomial moments?
Yeah. Then I'm not very familiar with his work, but there is some works of Vincent Vargas where he studies localization in these most heavy tail situations.
But I meant there is an exponential moment, but not all of them. Like
then
like exponential weight, for example.
yeah, no, on ZD at least everything works. I don't know if this exact thing will work through. I will have to think a bit, but on ZD everything works perfectly.
So in the strong disorder regime, do you have localization results?
Yes. So actually there is a very nice result by Ortgies and Mortars that shows something like the polymer measure is essentially supported on a tree which has an exponential growth which is strictly smaller than the whole tree.
But it's not quite localization.
On a single path. Yeah, I agree. I would have to check. But something that I can say is that, and something which is not true on ZD, is that if you see the free energy is essentially given by the energy of the maximal paths. And that's totally different from the ZD case, because on ZD, once you have one path with a huge energy, you have exponentially many paths which are close to it and which have essentially the same energy, so that adds an exponential factor. That's very specific to the tree.
Any other question or comment? Well, I have one. So, why you take the tree to be a fixed number of offsprings, and why do you? I mean, why the model is not? Because it seems on the proof, it seems, I mean, you have recursives.
Yeah.
This Martingale it will be recursive even if the number of children
It's random.
is random.
Yes.
And you will have a very similar.
Yeah, I think you can do that. Yeah. Yeah.
I mean, it will be more complicated.
Yeah, you have to check details, but
Yeah.
I think it works.
Well, if there is no any other question, let's thank again Gregorio.
Thank you.